When faced with a massive, tangled problem, a failing business, code base, or a medical mystery, our instinct is almost always to try and think harder. But raw mental effort against unstructured chaos usually leads to one of two outcomes. We either frantically guess at solutions, hoping one works, or we freeze completely, overwhelmed by the sheer number of moving parts. The issue isn't a lack of intelligence or focus. You cannot outthink a web of information just by staring at it longer. The confusion persists because the information itself lacks structure. Analytical thinking provides the ability to take a messy, interconnected situation and actively break it down into a coherent architecture of distinct, manageable parts. This functions as a procedural defense mechanism, a way to bypass the strict biological limits of the human mind. This animated diagram represents working memory, the brain's real-time processing center, where we hold and manipulate new information. Human working memory has a rigid biological constraint. It can only hold about 3 to 4 discrete chunks of information at any given time. Watch how this complex shape physically cannot fit into the grid. In cognitive psychology, the inherent difficulty of a problem is called its intrinsic load. When a situation has more interacting variables than those 4 available slots, the brain cannot process them all simultaneously. Cognitive overload originates in a hardware bottleneck in the prefrontal cortex. Once those 4 slots are full, the system stops accepting new input. To solve truly complex problems, we have to bypass this limitation. We need a systematic way to offload the cognitive weight. That offloading process relies on a precise 3-step cognitive engine. First is decomposition. Instead of swallowing the problem whole, break it down into parts. A failing business becomes traffic, conversion, and retention. Second is isolation. Focusing entirely on one variable shrinks the problem space to fit perfectly into working memory. The third step is relation. Once you understand the isolated parts, you map how changing one variable affects the others. This triggers a compression process. The brain bundles the information into a mental framework, a schema, and stores it in long-term memory. Because a schema acts as a single cohesive unit, no matter how much data it contains, it occupies only one chunk in your working memory. By continually decomposing chaos and building schemas, this 3-step engine artificially expands the brain's bandwidth. It compresses extreme complexity into executable units of thought. These studies, conducted by Herbert Simon, investigated how human expertise actually functions by comparing novices with professionals. Simon tested chess grandmasters by showing them real game boards for just a few seconds, then asking them to recreate the positions entirely from memory. The grandmasters reconstructed the boards with near-perfect accuracy, while novice players could only place a handful of pieces before forgetting the rest. But Simon introduced a crucial twist. He arranged the chess pieces completely at random, defying the rules of the game. Suddenly, the experts performed no better than the beginners. Their advantage disappeared. This proves the experts weren't using photographic memories. They were recognizing pre-built schemas stored in long-term memory. They saw functional groups of pieces, not individual pawns. Novices lack these schemas. They react to surface features, which forces them into a high-effort trial-and-error process of working backwards. Because they rely on schemas, experts allocate their time differently. They spend up to 40% of their problem-solving time analyzing and mapping the deep structure of a situation before they ever attempt a solution. True expertise is defined by perception. A beginner looks at a board and sees a chaotic noise of wooden pieces, but an expert perceives an organized underlying structure. In the professional world, these biological offloading mechanisms are formalized into strict frameworks to guarantee logical rigor. Management consultants use the MISI principle, mutually exclusive, collectively exhaustive, as a quality standard for decomposition. It ensures a problem is broken down without overlapping categories. Innovators use first principles thinking to isolate variables. By stripping away conventional assumptions, they work down to irreducible core truths, like evaluating the raw material cost of a rocket rather than accepting its market price. This exact same reliance on structure applies to computational analysis, specifically the architecture of large language models. AI researchers discovered a technique called chain of thought prompting, which serves as a direct artificial parallel to the human cognitive engine. By forcing an AI model to explicitly write out its intermediate reasoning steps one by one, its accuracy in complex tasks increases significantly. Enforcing structured, sequential logic is the universal prerequisite for avoiding errors, whether you are optimizing a human management team or directing artificial intelligence. This table visualizes analytical architecture across distinct professions. A consultant uses an issue tree to find root causes. An engineer traces execution paths to isolate bugs. And a physician uses differential diagnosis to eliminate diseases. The terminology varies by industry, but the structural engine is the same. Professionals rely on divide and conquer to manage complexity. However, this analytical mindset has a vulnerability. It assumes the system you are studying can actually be broken apart without destroying it. In environments known as complex adaptive systems, like global economies or ecological networks, the relationships between the parts are far more powerful than the components themselves. If you try to isolate a variable in a tightly coupled system, the process fails. Because of circular causality and delayed feedback loops, touching one element sends unpredictable cascades through the entire network. When the Schlitz Brewing Company decided to optimize a single variable in the 1960s by cutting production costs, the isolated analysis looked brilliant on paper, but it ignored the delayed systemic feedback of alienating their customer base, leading to the brand's collapse. A narrow analytical success can trigger what systems theorists call policy resistance. The intervention produces side effects that actively push back, creating outcomes entirely opposite to the original goal. Reductionist analysis breaks down when the whole system is greater and more deeply interconnected than the sum of its isolated parts. Purely algorithmic analysis lacks the awareness to recognize when an environment transitions from a linear set of problems to a complex reactive system. We saw this when companies attempted to use AI for resume sorting. The algorithm optimized for historical hiring data, replicating gender bias because it lacked the ability to evaluate the validity of its own objective. It followed the rules perfectly, but couldn't recognize that the rules were producing a flawed outcome. Metacognitive control functions as the executive layer that monitors these reasoning strategies. It provides the perspective to recognize when a model is failing, and it triggers an immediate shift in approach. True experts use metacognition to identify when an analytical strategy is reaching diminishing returns. In the Schlitz case, this would have meant recognizing the cost metric as a poor proxy for long-term health before the system collapsed. As artificial intelligence automates the sequential steps of logic, the human role transitions toward the design of the structure itself, defining the boundaries and validating the ethics of the patterns found. We use analytical thinking to cut linear problems down to biological size. But we must ultimately wield systems thinking and metacognitive control in order to master a complex, non-linear world.